Let's park the phased array for a minute, get back to basics, and talk about AWS inspections. First off, thanks to my buddy Will Wagner for getting me this really cool Canadian hockey jersey. I wore that to the UT competition at the BINDT show in Telford, United Kingdom a couple weeks ago, and I lost the competition. Lots of really good people there, but we all lost to the one and only Ray Wilson from Array Training. Way to go, Ray. There are a few things that define AWS inspections, none more so than the giant transducer. They are low frequency, 2 1/4, usually square, either 5/8 by 5/8 or 3/4 by 3/4, and they're mated to these absolutely gargantuan wedges. I call this one the big red brick, banana for scale. You can also get them in a snail shape. 2, you have procedure tables that tell you exactly what angle you're allowed to use based on the geometry of the joint and the thickness. And we don't use a TCG or a DAC like we would in the ASME world. We actually set up on one side rolled hole in the IIW block, and then we calculate the attenuation manually by assuming that after the first inch of sound path, it attenuates at 2 decibels per inch. The indication rating, or how bad is that thing in the weld, we represent that with the letter D. We have an equation to solve for the indication rating that's D equals A minus B minus C. A is your indication level, B is the reference level, and C is the attenuation. The way this code is written has remained relatively unchanged since about 1969. First thing we're going to do is set the velocity and the wedge delay, but oh, wait a minute, velocity, we kind of already know that number. There's really no reason for you to be messing with that number, so let's leave that at 1280 inches per microsecond. Now we're just going to put it on an IIW block here. We'll hit the 2-inch radius. I'm going to move this back and forth till I peak that signal. Then I'm going to adjust the 0 offset or the wedge delay to make sure that that gate 1 indication peaks up at the appropriate distance. But before we move on, this is where we get our beam index point from. So you can see that when the signal is peaked, now I can put my ruler down and measure that the X offset is 1 1/8 inches. From here, I'll take the IIW block, I'm gonna flip it around, and we're gonna determine the angle. Get that reflection off of that big hole, peak the signal right around here, and if I compare that to where I know the beam index point is, I can see that that angle is just about 70 degrees. Now what we need to do is set the sensitivity. We do that on just the one hole, no TCG, no multiple holes, just the one shot. Put it down, peak that signal, and oh, wait, stop right here. In ASME land, we do our full screen height, our reference level is at 80%, but on AWS, they want you to do it from 40 to 60%. So I'm gonna go into my menu here, and I'm gonna change that number to 60%. Now I will peak that signal up on the instrument, and then I will call that the reference level. Now we're ready to go, right? We're gonna take it down here and start scanning the weld. Not quite. We have to add scanning gain like we would for any manual inspection. How much gain you add is based on the loading condition, whether it's static or cyclic, and how much sound path you're using. I've got a 5/8 inch plate. I'm going to pretend that it's statically loaded. I need about 5 inches of range to get down to the bottom and back up to the top again. So if I turn around and go back to the AWS code and look at the table, it tells me that I need 19 decibels of scanning gain. I'll come up from the center of the weld. You can see that root indication keep popping up, and then there's something right in front that gets a little bit messy. I happen to know that's the crack on this plate, so let's zoom into that and try to isolate it. Set that back down to 60% screen height, which is our reference level, and then I can hit freeze. A is the indication level. I needed 57.9 decibels to bring it up to that spot, so 57.9 is my A value. B was the reference level, which was actually 59.2. We did that when we set up on the side drilled hole. We calculate the attenuation factor by taking the sound path in inches, subtract 1 inch, and then take the remainder, multiply that by 2. You write that all down on your report and you manually calculate the indication rating D, or if you have the software on your instrument, you let it do it for you. In AWS land, a smaller defect rating actually means a worse flaw. If we look at the acceptance tables, you can see that something that is a class A has a lower rating than something that is a class D. My defect rating is minus 3.4 decibels, which if we compare that to the table is way worse than a Class A, because a Class A for a 5/8 of an inch weld is actually at plus 5 decibels. So we are way below that. We're way into a Class A, and a Class A flaw, you're not allowed any length at all. To measure the length of the flaw, I think by now you've heard enough from me about 6 dB drop, about how I think that's not very good. Fortunately, AWS does not follow that strictly. What it says in the code is the length shall be determined where the indication rating amplitude drops 50% or 6 decibels below the rating for the applicable discontinuity classification. So this guy's an A, so we're going to move it back and forth, and we're going to mark out the A bits. But it also says, where warranted by discontinuity amplitude, the procedure shall be repeated to determine the length of Class A, B, and C discontinuities. All that means is that if it's an A, you just keep going until you got rid of the B part and the C part as well, and you mark all of those out. And that is kind of a general overview of the AWS technique. I hope you found this video useful. If you did, please hit the like and subscribe buttons, and go Canada.